So in the last video, we looked at Fermat's theorem, and I wanted to make several remarks with you about this. So I've kind of written them down a little bit to save some time, but I'll add some details here as well. So the first one is that the converse is false. And let me just take a moment and give you some context to the converse. Some of you might not have heard that word before. So anytime you see a statement, an if statement like P implies Q, or if P, then Q, the converse is Q implies P. That's what the converse is. If you've taken discrete, you've seen this. And so anytime a mathematician writes down a conditional statement, the question that always pops into their head is the converse true? Is it an if and only if? And the answer for Fermat's theorem is no. Just because the derivative is zero at a point doesn't mean necessarily that you have a local extrema at that point. You might not. And so let me give you an example to illustrate this. This is sometimes called a counterexample. This is a counterexample to the converse of Fermat's theorem. Here it is. If I have f of x is x cubed, then f prime of x is 3x squared. All right, I'm going to solve. How is this? Where is this zero? You can see it yourself, actually. If f prime of x is 0, then x is just 0, right? So certainly f prime of 0, the point is f prime of 0 is 0, right? But if you go to graph this, wow, my lines aren't lining up. If you graph x cubed, hopefully you know what it looks like. It looks like this. And when you go look at 0, I don't care how far you zoom in, you're not going to see a local min or a local max there. There's no local min or max there. So converse isn't true. Sadly, it would be awesome if it was, but it isn't. All right, so next statement is just because the derivative doesn't exist doesn't mean that there's not a local extrema there. You might have a local extrema where the derivative doesn't exist. And let's look back up at Fermat's theorem. Fermat's theorem says if you have a local extrema at a point, if you do have one, and the derivative does exist, then f prime is 0. It doesn't say anything about when the derivative doesn't exist. And so you need to realize that these local extrema, local mins and maxes, can happen at places where the derivative doesn't exist as well. And so let's see an example of this. Let's use a bright color. So let's consider f of x equals the absolute value of x. We've already done in class, if you look back in your notes from chapter 2, we've seen that f prime of 0 doesn't exist. Does not. I should probably use capital letters for that. I don't know why I did lowercase. It does not exist. And you can draw the picture, and the picture actually kind of reveals all, although we showed f prime of 0 doesn't exist using limits. But if you graph absolute value of x, it looks like this. And immediately you see two things. One is f has a local min at 0, and in fact an absolute min at 0. And yet, because there's a cusp here, there's not a unique tangent line. And so there's lots of tangent lines, right? You can imagine infinitely many tangent lines here. And so there is no derivative at that point. So two big takeaways, right? The converse of Fermat's theorem is false, and local extrema can happen where the derivative is undefined. And so with that in mind, I want to give you a definition. We're interested in finding all possible points where local extrema could happen. And then we'll go through and study those points. So here we go. So assume f is defined on an open interval containing a point c. This is x equals c. The point is c is not an and. I don't know why I keep writing ands instead of ands. C is not an endpoint. Okay, this is x equals c. Then we're going to call x equals c a critical point. Critical point for our function if either f prime of c equals 0 or f prime of c doesn't exist. And what Fermat's theorem really says, let's just say moral, what Fermat's theorem is really ultimately saying is that local extrema occur at critical points. So just because you're a critical point doesn't mean you're local extrema. But if you are local extrema, you have to happen. You have to occur at a critical point. And so the key question is, how do we classify critical points? Some critical points, like we saw for x cubed, are going to be no local extrema. Others are going to be local mins. Others are going to be local maxes. How do we tell whether a given critical point, what it is? And the answer was in the next video. We're going to have a test that's going to help us see.